Hello, in this session we'll go with group 15 elements. Fifth A group elements also called nicogens. Their compounds cause suffocation, that's why they are called nicogens. And the compounds are called nicomides. Nitrogen, phosphorus, arsenic, antimony and bismuth. General electronic configuration is NS2NP3 where N is equals to 2 to 6. Ionization potential values are more than 60 A group elements due to half-filled electronic configuration. Oxidation states -3 and +5. These two states stability down the group decreases. Negative oxidation state and higher oxidation state stability down the group decreases. Lower oxidation state +3 stability down the group increases. Nitrogen can show -3 in ammonia, -2 in N2H4, -1 in NH2OH, -1/3 in hydrozoic acid, 0 in nitrogen, 1 in N2O, 2 in NO, 3 in HNO2, 4 in NO2, 5 in HNO3. So nitrogen can show these many variety of oxidation states. Nitrogen, phosphorus both are non-metals. Arsenic, antimony are metalloids. Bismuth is a perfect metal and bismuth is a conductor. Catenation. Phosphorus catenation is more than nitrogen than arsenic, antimony, bismuth. Nitrogen contains actually a triple bond elemental state. If you see N2 gas, N triple bond N, the bond energy is 946 kilojoules per mole, whereas phosphorus, arsenic, antimony are tetraatomic solids. P4, you can see all the phosphorus atoms are at the corners of tetrahedron. Bismuth is monoatomic solid. Here one important point you remember, nitrogen single bond energy, phosphorus single bond energy, if you consider, phosphorus single bond energy is greater than nitrogen single bond energy. Note, phosphorus single bond energy is greater than nitrogen single bond energy. Allotropy, nitrogen, solid nitrogen can show alpha and beta forms. Gaseous nitrogen cannot, but solid nitrogen can show alpha and beta forms. Phosphorus can show white, yellow, red, violet, black phosphorus. Different colors are there. Arsenic and antimony, they show yellow and gray colors. Bismuth, as it is a metal, it doesn't show any kind of allotropy. When we see the compounds, the first one is hydrates. Hydrates are very, very interesting, very important. Thermal stability of hydrates down the group decreases. So ammonia is more stable. Lewis base character, bond angles, dipole moments also same order. Ammonia greater than phosphine, then arsine, then stibine, then bismuthine. Lewis base character, thermal stability, bond angles and dipole moments. Ammonia bond angle is 107 degrees. Phosphine, arsine, stibine, bismuthine all will be around 90 degrees due to the participation of pure p orbitals. In ammonia, sp3 hybridization is there. In the remaining, there is no hybridization concept. Reducing character down the group increases. The reason for this is the stability decreases, the bond energy decreases, the bond length increases. So reducing character down the group increases. One very important point to be noted. Halides, if you see, MX3 type of halides, they are called trihalides. MX5 type of halides, they are pentahalides. sp3, MX3 type of halides are sp3 and pyramidal. Example NCl3, PCl3, BaCl3. Their stability of NF3 is greater than NCl3 greater than NBr3. Ease of hydrolysis, NCl3 is easily hydrolyzed than PCl3, ACl3, so on. Lewis base strength down the group increases. NF3 when you compare NCl3, NBr3, NH3, NH3 is much better. Lewis acid strength, PF3, PCl3, PBr3, PI3. Lewis acid strength is more for phosphorus trifluoride. NCl3 and hydrolysis produces HOCl, but PCl3 forms H3PO3. There is a difference, you see. NCl3 is giving you ammonia and HOCl. PCl3 is giving you H3PO3, and bismuth is very special, it gives you BiOCl, bismuth oxychloride. When it comes to pentahalides, okay, like NCl5 is not possible because nitrogen cannot form 5 bonds, so NCl5 is not there. PCl5 is possible, trigonal bipyramidal sp3d hybridization, and solid PCl5 exists like PCl4 plus and PCl6 minus. PCl4 plus is tetrahedral, PCl6 minus is octahedral. PCl5 immediately turns into PCl3 and Cl2. PCl5 is having two different types of bond angles, so it always tries to convert into either sp3 hybridization or sp3d2 hybridization. As it can release chlorine, it is also called a chlorinating agent. Bismuth also cannot form pentahalides easily, only pentafluoride is possible. That is because of its inert pair effect concept. This is about the fifth group elements introduction lines. Then oxides. Trioxides and pentoxides both are there. N2O3, P2O3, AS2O3 are acidic. Acidic nature decreases like this. Sb2O3 is amphoteric and Ba2O3 is basic. Whereas pentoxides, if you see, N2O all are acidic only. Here no basic. Trioxides, Ba2O3 is basic, but in pentoxides all are acidic only. Acidic strength down the group decreases. N2O5 is more acidic. Nitrogen oxides are very special. N2O is neutral in nature. NO is also neutral in nature. Remaining all are acidic in nature. N2O, NO, N2O3, NO2, N2O4, N2O5. N2O is also known as laughing gas. It is used as anesthetic. It is diamagnetic. NO is paramagnetic. It is oxidizing agent and reducing agent, both it can function. It is generally formed because of thunders and lightning in the atmosphere. N2 plus O2 gives rise to NO. Otherwise, it can be prepared by the oxidation of ammonia. NH3 plus O2, you will be getting the NO. N2O can be prepared from ammonium nitrate. NH4NO3, when it is heated, N2O is formed. NH4NO2, when you are heating, nitrogen is formed. NH4NO3 gives you N2O. NH4NO2 gives you N2. N2O3 is nitrogen sesquioxide. It is a combination of NO2 and NO. NO and NO2, when they are heated, it forms N2O3. N2O3 is diamagnetic. NO2 is paramagnetic and reddish brown color gas. Because of the presence of unpaired electron, it is colored and paramagnetic. NO is colorless paramagnetic. It is color and paramagnetic. N2O4 is dimeric form of NO2 and this is diamagnetic. N2O5 is anhydride of nitric acid. It can be prepared by from HNO3 by using any dehydrating agent like P2O5 or P4O10, you can say. So oxidation states are gradually increasing from +1 to +5. As the oxidation state increases, the acidic character also increases. Phosphorous oxides, two types of oxides we discussed. One is P4O6, second is P4O10. P4O6 is anhydride of H3PO3. P4O10 is anhydride of H3PO4. In the previous we were discussing N2O3. N2O3 is anhydride of HNO2. N2O5 is anhydride of HNO3. NO2 or you say N2O4 is the mixed anhydride of HNO2 and HNO3. So P4O6, P4O10. P4O6 will be having a structure of 4 corners of tetrahedron occupied by phosphorus. There is no phosphor-phosphorus bonds. Okay, na? All bonds are POP bonds only. There are 6 POP bonds and 12 sigma bonds and 16 lone pairs are there in P4O6. When you see the P4O10, that will be containing 20 lone pairs and there are 6 POP bonds. All phosphorus atoms are at the corners of tetrahedron. There is no direct PP bond. You can see the structures here. P4O6 and P4O10 structure, there is no PP bond. All bonds are POP bonds only. NCRT, you can see double bonds are generally mentioned as single bonds only, like dative bonds and all. Oxoacids of nitrogen. Hyponitrous acid is H2N2O2. It's a dibasic acid. OH and double bond NOH. Unstable. Rarely we can see this. Nitrous acid is very important. HNO2. It is because of intermediate oxidation state. It is an oxidizing agent as well as reducing agent. It's a monobasic acid. Bent shape. sp2 hybridization of nitrogen. Nitric acid HNO3. It's a good oxidizing agent. It is also monobasic. It is trigonal planar. Iron, chromium, nickel, aluminium become passive by HNO3. HNO3 properties. HNO3 makes iron and all passive due to the formation of oxide layer. 3 volumes of HCl and 1 volume of HNO3 is aquaresia. Aquaresia, in which gold and platinum are also soluble. When sugar is treated with HNO3, it turns into oxalic acid. HNO3 is also called aqua fortis. It is used generally for the cleaning of lab utensils. Per nitric acid formula is HNO4. HNO4 and nitric acid structures are almost same. One extra oxygen bond will be there per nitric acid. Oxo acids of phosphorus. These are very very special. Hypophosphorus acid, phosphorus acid, phosphoric acid, or you say orthophosphoric acid, then metaphosphoric acid, pyrophosphorus acid, hypophosphoric acid, pyrophosphoric acid. See the formula, and here structures are also I mentioned. Structures are important. You see the structures. H3PO2. There are two pH bonds. If pH bonds are there, that's a reducing agent. And there is one OH group, so it is monobasic. One salt is possible. H3PO3, two OH groups are there, so it's a dibasic. pH bond is there, so reducing agent. H3PO4, three OH groups, tribasic. HPO3, unstable. It generally happens in the form of cyclic trimer. Here HPO3 contains one OH group, so monobasic acid. But trimer is a tribasic acid. H4P2O5, it is again dibasic acid. There is a pop linkage POP. It contains pH bond, so it is definitely a reducing agent. H4P2O6, four OH groups are there, so tetrabasic acid. H4P2O6, H4P2O7, POP bond is there, remaining all attached by OH groups. These are the acids: pyrophosphoric acid, hypophosphoric acid, pyrophosphorus acid, metaphosphoric acid, and all.